We are talking about optimization problems, all right? This is sort of how do I choose this to get the best out of this, the most of this, or something like that. I just had two more examples to do, and I want you guys to try one. Optimization. All right. What? Optimization. Let's just do another one. I will remind you, I had sort of some very simple steps to follow. I'll just write those again. So the first step was just sort of, these are always going to be some kind of word problem, and that you have to, oftentimes it takes a lot of work just to set up the equations and everything. First I would say decide what should be maximized or minimized. Right? What exactly is the thing? Is it a volume of something, an area of something, whatever? Decide what should be maximized, minimized. Then you want to write that thing. Write it as a function of a single variable. And actually, this step right there is usually the hard step. This can involve using some kind of geometry formulas. As usual, I will not expect you to have obscure geometry formulas memorized, but you should know area of a circle, area of a triangle, Pythagorean theorem, those kinds of things. Nothing too fancy. So you write your thing as a function of a single variable. Then you need to find the interval of allowable x values, or whatever you want to call your variable, right? And then the final step is to actually do the calculus of finding the absolute maximum or the absolute minimum, whatever it is. Do the absolute maximum or minimum. Remember, that requires a function and an interval. So you need to have done the previous two steps are just trying to set you up for that last step. Do the absolute maximum minimum thing with the derivatives and all that. This is what some people refer to as the math. Sometimes people say, oh, I did everything right, I just messed up the math. I think what they mean is like I added some numbers together wrong. My response is always, that's not really the math, that's just like adding the numbers up. The rest of it is the math. Anyway, you do the absolute maximum using the calculus. Okay, let's try. Like I said, I got an example, then I got one for you to try, and then I wanted to just do one last harder one. How about this? I'm building a fenced-in area, not a true story, like this. A big rectangular area that's divided into 4 regions. I don't know if that looks like a square. It's not supposed to be a square. It's just a big rectangular fenced-in area, which is divided into 4 equal parts. All right, so that those bars, those fences going through the middle, they do actually go directly through exactly halfway down the middle. All right, and I have I'm having problems. I got a new computer, but all my issues are with the iPad. My hand is doing weird things. I have one of those. This pencil came with like a silk glove with only 2 fingers on it. Have you seen that? It's meant so that you can rest your hand on the screen without making it look funny, but I feel weird about wearing a silk glove with 2 fingers. I don't know. I'm sure I could pull it off. I have only, here's the deal, 300 feet of fencing, all right? So all of those parts of the fence have to be made up of 300 feet total of fencing. And the question is, what's the biggest area that I can enclose in this way? And how exactly how big this thing should be to obtain that area. What's the biggest area I can enclose? And which dimensions will get me the biggest area. Which dimensions achieve that area? All right. Using 300 feet of fencing. Okay. Let's try and do it. So, just going through the vague, 4 steps. The first step is decide what in this problem is supposed to be minimized or maximized. This is usually very easy, just obvious from the way the question is being asked. I want to maximize the area, right? We'll maximize the area. Next, and this is typically the hard step, write a formula for the area in terms of only one variable. Now, this is going to take a bit of doing. I'm actually going to start by looking at that picture that I have there and assign perhaps more than one variable to it. Eventually, we want to boil it down to only one variable, but I'm just drawing the same thing again. It seems to me there are actually 2 variables here. Because I said it's not a square, there's this distance across, and then there's this distance here, all right? I'm going to give those 2 different variable names. So let's call the distance horizontally, how about let's call that x, and how about the vertical distance? I will call y, all right? Now eventually we need this to be in terms of one variable, but we got to start somewhere. And I think based on those 2 variables, it's not hard to write a formula for the area. The total enclosed area, what do you say? Someone want to shout it out? This is not a hard question to answer. X times y, yes. This is a big rectangle, and its area is xy. All right? The hard thing is trying to write this in terms of one variable. So in order to do that, we need to write really y in terms of x. My intention is to figure out what y is in terms of x and then just sort of replace this y with a more complicated thing in terms of x so that it'll be all written in terms of one variable. And how would we do this? Write y in terms of x? Well, there's one more bit of information in the problem, and that is that the entire, that I have 300 feet worth of fencing to work with. All right, so what does that have to do with anything? 300 feet of fencing. Can anybody say, based on the x and the y, what does that mean about the 300 feet? Something about all that amount of fencing has to add up to 300. Can I say? Yeah, what do you think?
Can't you make your formula 300 equals x times y, then solve for y?
300 equals x times y. It's not x times y, because that would be the area. 300 is the distance of fencing that I have. So it's really this distance, and it's the perimeter plus those 2 extra bits, right? That's what the 300. Any other idea? I hear something from over here. I heard something. What do you think?
You need to use the perimeter formula.
Yes, it's the perimeter. Actually, it's not just the perimeter, but it is the perimeter plus also this fencing across the middle, right? But anyway, what would that be?
Could you do 3x plus 3y?
3x plus 3y. Yeah. It's 3x because it's like this, and then this, and then this, right? There's 3 lengths of the horizontal distance, which is x, and then plus 3 lengths of the vertical distance, which is y. So, yeah, 3x plus 3y equals 300. That's what she said, I think. 3x plus 3y equals 300. Right? That's what she said. Remember when people used to say that? Yeah. That was so hilarious, wasn't it? Okay, remember, my intention with this formula is to solve for y in terms of x and then plug it back into something from earlier. So maybe just to make things easier, we could divide everything through by 3 here. It just says x plus y equals 100, and then I can solve for y. Y is 100 minus x. And now I'm ready to write a in terms just of x, right? A is x times y, and then I'm going to stick this in for the y here. So, and I'll write this now like a of x, right? It is now a function of only one variable, and it's going to be x times y, which is x times 100 minus x. And just because I know in the next step I'm going to be taking the derivative of this, I'm going to distribute there, just because this is more convenient to take the derivative when it's written this way. All right? And this is a pretty simple formula as far as, calculus goes, right? This is easy to work with for taking derivatives and such. Okay, that was the hard part of this problem. All that work to get to this formula. What comes next in my four-step process was find the interval of x values. What's the smallest that x could be? What's the biggest that x could be? Now, in this example, you want to really, in terms of like how big could the x possibly be, it really has to do with that 300 figure, right? The x can't be 1,000,000 because I only have 300 feet of the fencing. Really, if you look right here, and in fact right here is even better, x plus y equals 100. Right from there, you can see, I think, what the smallest or the biggest possible value of x must be. So I'm going to say, just remembering, x plus y equals 100. The smallest x is, oops, get out of here, sorry. X equals 0, and then the y could be 100. Or it could be the other way around. The y could be 0, and the x could be 100, right? If I'm looking at this formula right here, x plus y equals 100, you can just think in terms of what if I max out the x versus what if I max out the y. This will tell you how big or how small. The smallest x is x equals 0, and the biggest x is x equals 100, and this occurs when y was 0, right? If the y is 0, then the x will be 100. If the x is 0, the y will be 100. All right? Anyway, my interval then is the interval from 0 to 100, right? And now I think we're ready to do the math, right? This has all been math so far, but now we're just going to do the routine sort of calculus of finding the absolute maximum. All right, I hope you remember the general procedure. You find the critical numbers, which is when the derivative is 0 or does not exist, and then you plug into the original function all critical numbers plus all interval endpoints. So I'm going to do the critical numbers first. Remember, a of x was 100x minus x squared. For the critical numbers, I need to take the derivative. It's going to be 100 minus 2x. And then I set that equal to 0. For the critical numbers, 100 minus 2x equals 0. 2x equals 100. X equals 50, right? So this is my only critical number. And then I'm just going to plug a bunch of stuff in. I'll go a of 0 and 100 were my two endpoints, and then I also go a of 50, right? And the formula, of course, was a of x equals 100x minus x squared, right? Now for the 0 and 100, you can plug them in if you want to, or you could just remember the setup here. If x is 0, then the total area is going to be 0. And also if x is 100, then the y will be 0, and so the total area will be 0. These two both give you 0. You can actually just, calculate those values in the formula, or just sort of by a common sense geometry. Those areas have to be 0 when either the x is 0 or the x is 100, making the y 0. Anyway, this one is the most interesting one, a of 50. It's going to be 100 times 50 minus 50 squared. And this I did in my calculator. I got 2,500. Probably could have done that in my head. All right. All right. And then what's the maximum, right? These are the values. Remember how you do this? You just look at all the answers here and you compare them and choose the biggest and the smallest. Now in this problem, I don't care about the smallest. I do care about the biggest, and it's that one down at the bottom. So the maximum area, the biggest possible area is 2,500. I guess this would be square feet. I had a challenge. This is a true story. In my own personal life, last night, my wife decided it's time to buy a new laundry basket because our old one is like falling apart. And she's looking on the Amazon. She says, this laundry basket that I'm looking at on the Amazon is 77 liters. Is that bigger or smaller than the one we have? My answer was, I have no idea how big 77 liters is, but I got out the tape measure. I measured the old one. I did a little geometry, and I figured out. The old one was like 53 liters or something, so this one's bigger. That's my story. I don't think she was very impressed. It wasn't all that impressive, though. Okay, remember the question that I asked in particular in this problem, what's the biggest area I can enclose? And also, what are the dimensions which give you that area? So what exactly are the dimensions which give you this area? So I'll just say this happens when x equals 50 feet, because that's the number that came from x equals 50. If I want to tell you all the dimensions, I should also tell you what the y is. When x equals 50, and what would the y be in that case? Well, if you look up, you will see this several times. X plus y is 100, or you could say y is 100 minus x. So if x is 50, then y is also 50, right? Because y is 100 minus x. So y equals, I'll just write it out, 100 minus x, which would be 50 feet also. So the biggest area in this problem occurs when the shape as a whole actually is a square. That gets you the biggest area, 50 by 50. All right. That's that. Any questions about this one? No. All right, I got one. Just a simple variation of this problem that I would like you to try out. It's the same problem, but like this. Like that. All right? Still, those four little bits are the same size as one another. Same question, though. What's the biggest area I can enclose? And what sizes of those things will get you the biggest area? All right? And a little spoiler. It's not going to be x equals 50 anymore. It's actually changing it around in this way actually makes it different. Could we talk actually about what's it? Is this even different at all? Didn't I just move this piece like from here to here? Is this actually, anybody see, is there any real difference? The answer is yes, there really is a real difference. But, yeah?
Well, because your y value changed.
I guess, when you work through the details, it will look different, but can anybody say, like, just by looking at the picture, do you agree, like, isn't this just the same where if I just move that guy back up here, then it'd be, yeah.
No, if you, take it out, the bottom, or the left and the bottom fence, there's, extra of those.
Yeah, it's because this piece, if you draw it over here, it has 3 lengths of fencing around it. Whereas if you draw it in this position, it gets to share 2 lengths with this one. And so the total perimeters will actually add up differently in this configuration than in the previous. So you should expect to get a different answer. All right? See what you think. I would like to make a little suggestion. In this problem, it's a little easier to set up if you call this the x. And I'll let you think about what you should call the y. Just because you'll see when you add up the perimeter, it's a little easier to consider it this way as the x, rather than x being all the way across. That's my suggestion. feel free to chat with your friends about it.
solve for y, they would say like x equals that
That's
value.
gonna equal 300 and then you just substitute.
So total area is 50, right? Other formula,
Would it be 6y plus 7?
total fencing.
1, 2, and then that's 4y, 6y, and then 1, 2, 3, 4, 5, 6, 7.
Y equals 50 minus 76. We would plug it all into the area.
That's good. Yes.
So that would be a.
Oh shit, you find a prime area.
Then we need to solve for y. The perimeter, oh, yes, right.
No, it doesn't.
That can simplify. Because 4 times 7 is 56. Right, I'm just scared.
Where? Oh, so wait, what do you get for the range? It says 27 range over 6. Where's the square point?
I don't know. Because you had to friggin' distribute the x and distribute the
Why
y.
is the x up there?
Because now it's this is x and this
Oh,
is y.
fuck, that's such bullshit.
So you've got 4 times x times
I never like problems that one.
How do I say it?
and then I just did 3 x.
14 thirds.
And then multiply by.
No, I'm pretty sure that's right. Okay.
Oh, yeah, it's probably
So did you
All right, let's talk about this one. I don't know if you finished already.
No, I got 7x.
It's all right if you didn't.
is the same as this?
All right, let's try it out. So when as I was going around, I never told you how to choose the y, but I think it is sensible to choose the y to be this distance, right? That makes everything easier. You could choose the y to be the entire vertical distance, but that makes the area formula more complicated. Anyway, in terms of x and y, what did you get for the area here? I know many people got something. Yeah. 4xy, yeah. X times y is the area of just one of these blocks, and there are 4 of them, so the area is 4xy. We need to go to some effort to express the y in terms of x so that we can get this in terms of a single variable. But the other piece of this business is that I have 300 feet of fencing. This tells me something or other adds up to 300, right? And what you have to do is you count how many lengths of length x am I using in this diagram? I see 1, 2, 3, 4, 5, 6, 7, right? So there are 7 x's. And how many y's? That would be 1, 2, 3, 4, 5, 6 y's. So the correct formula to use for this sort of fencing, it's kind of like a perimeter measurement, would be 7x plus 6y, right? This unfortunately has some not so nice numbers in it, but this is what we're going to solve for y in terms of x to simplify the area formula. So from here, I'm going to solve for y. It's going to say 6y equals 300 minus 7x, and then divide by 6. That's 50 minus, you get this 7 over 6 times x. All right. That 7 over 6 is annoying, but we can handle it. We got calculators, right? You do at least. All right. That's the y. So plug this into the area formula over here, and it'll say a, I'll write a of x this time, is 4x times y is 50 minus 7 over 6x, like that. And as usual, I'm going to distribute that just so to make the next step, the derivative part, easier. So distributing the 4 gives me, I guess that's 200x minus 7/6 times 4 is 28/6, which is 14 over 3. Is that right? X squared. Anybody agree with that? I think so. Some people do. All right. This is my formula for the area. All right. Eventually, I'm going to do the, take the derivative of that, etc. What about the critical numbers? No, not. What about the interval endpoints? That's what I wanted to say. So look again at this formula. 300 equals 6. It was 7x plus 6y, right? I'm going to look at this to decide what's the smallest the x could be versus the biggest the x could be. Now, if the x was 0 here, well, that's the smallest that the x could be. So the smallest x is 0. What about the biggest? The biggest x will be when the y is the smallest, right? These things, they have to add up to 300. So if I want the x to be the biggest, that happens when the y is the smallest. So the biggest x will be, this is what I meant to write there, be when the y is 0, right? And so it'll say 300 equals 7x, x equals 300 over 7. That's the biggest possible x value, which is 40 something. I saw some people put that in your calculator. All right. So let's make the interval. But anyway, this number is not really important because when the y is 0, I know the total area is going to end up being 0 anyway. So like whatever this number is, I'm not actually going to have to calculate it. So the interval, anyway, the interval is 0 to that number, 300 over 7. All right. And now let's do the calculus part. That is the critical numbers. So first of all, the formula itself was, I forgot, it's that in the box. 200x minus 14 over 3x squared. All right. Do the derivative. A prime of x is 200 minus 14 over 3 times 2 will be 28 over 3 x. And then we solve this for x. Set this equal to 0. 200 equals 28 over 3x. X equals, did anybody do this on a calculator? I don't have mine. What do you get for the x here? Nobody did? We got this far? Or 9.3 repeating?
Yeah.
I think I buy that. Yeah, I guess. Well, that's what 28 over 3 is, isn't it?
Oh, yeah, sorry.
So this is 9.3 repeating equals 200. And then you divide that.
150 over 7.
150 over 7?
Yeah.
That's what I got too.
Okay. Can you just divide that for me? Rather than, I mean, I suppose I could have done that with the fraction.
66.66 repeated.
66?
No, I think it's 21.42.
All right. That sounds better to me. 21.42?
8, 5, 7.
Yeah, all right. Thanks. Okay, great. I like the sound of that. So anyway, this is my critical number, right? Plug everything in. That's going to be the answer, really. We have to verify that it indeed gives you the maximum area, but I already know the two area, the interval endpoints, 0 and that other number, 300 over 7, they both give you 0 areas. So this other number must be the right one, 21.42. And what's the area there? Did somebody do this on your calculator? Nobody did. Does anybody else care about that number? Whatever it is, this is the maximum. It's not 0, right? It's bigger than the others. Did you calculate it?
Yeah.
Yeah, what is it?
214.28.
Great, thank you. Yeah, this should be square feet, right? Just out of curiosity, you could compare this with the previous problem. In the previous problem, the answer was, where is it? Here, 2,500 square feet, right? That's how big you can make the area in the previous problem. This one is totally different. This must be wrong. Did anybody else type this into their calculator? You should be doing 4 times x times y. Sorry, I didn't go through all the numbers ahead of time like I usually do. Welcome back. It's a train wreck in here. This can't be the correct answer. You should be doing do this with it, right? 200x minus 14 over 3 times x squared. Maybe it was that number times 10? I don't know. I see some people hitting the buttons. I appreciate it. What'd you get?
I got 2,142.
Okay, I like that. Was that just 2,142?
Point, 8.
Like this number times 10? Or times 100? Is that a coincidence? All right, I have 10% confidence in these numbers. I'm not sure what's happening with all the calculating, but this actually seems kind of reasonable to me. Like I would expect the answer to this question to be close to the answer to the previous question, but a little bit smaller. If you want to make the fence in this weird shape, you're going to be able to make it pretty big, but I would assume not quite as big as the square arrangement, which is more efficient because you have more sharing of the fencing. All right. Sorry, I didn't run these numbers myself ahead of time. Anyway, that right there is the maximum, or whatever that number is supposed to be, is the maximum area that you can enclose. All right. I see a lot of people typing into their calculators. Anybody agree or disagree with this number? Or maybe you're texting your friends about what a nightmare this is. That's all right too. All right. Okay, I think I'm done with this problem, if that's all right with everybody else. I expected, the area that I get at the end should be comparable to the previous problem, but I would expect it to be a little bit less because of the weird shape of the fencing. All right, excellent. We got about 15 minutes left. I wanted to do, I was going to do one more of these, but now I'm feeling like, why don't we just move on to the next section? We actually only have one more section in the book involving the derivative. Then we're going to move on to, we're going to stop talking about the derivative, really. We're going to talk about something called the antiderivative, which I'll say is totally different. Although you'll realize pretty quickly, I guess it is totally different, but it's kind of similar. But anyway, before we talk about that, one last section before finishing off with the derivative forever, and that is something which I'm not sure you have heard of in high school. Newton's method. Newton's method. This is the last section in this chapter in the textbook, the last topic involving the derivative. Newton's method is another method for approximating stuff. You know, we had the linear approximation that we did like 2 weeks ago. on the quiz, I asked you something like approximate the square root of 82. And the idea of that is you know what the square root of 81 is, and 81 is right next to 82. And so you can do this thing about drawing the tangent line or whatever. That's called the linear approximation. Newton's method is actually much better as a general purpose method for approximating things. Newton's method is better. But it only is used, so this is another method for approximating stuff, and it's used to find, what I mean by find is approximate, I'll say it that way, used to approximate x values where f of x equals 0. So it can only be used to find values where some function equals 0. Which means if you want to do this to estimate something like the square root of 82, you have to be a little cute about how you choose the function. In that case, you wouldn't choose the function to be the square root function. You would choose it to be more like the square root of x minus 82 or something. And then you want to estimate what makes that 0. But anyway, Newton's method, it can be used in general to approximate anything that you want. But we are only going to focus on this thing. It's used to approximate x values where f of x equals 0. This is called the roots of f of x, right? In general, the word root, usually when people say root, they mean something like a square root or a cube root. But in this context, the root of a function means the points where that function equals 0, all right? The most popular, everybody knows something like the quadratic formula. That's a formula for telling you the roots of a quadratic polynomial. Newton's method you can use to find the root of anything that you want. Here's the idea. I want to try and do I'll just draw pictures for a simple example. Let's find, I put extra apostrophes in there. Let's find a root of this polynomial, x squared minus 2 equals 0. Sorry, I have to write it as a function. F of x equals x minus 2. All right? The roots are the places where this function equals 0. So we are finding where x squared minus 2 equals 0. Now, in reality, that is the square root of 2, right? That's the number for which x squared minus 2 equals 0. If you wanted the square root of 82, you would use the function x squared minus 82, right? We are finding where x squared minus 2 equals 0. Graphically speaking, Newton's method is based on looking at a picture. If I were to draw the graph of x squared minus 2, it looks like an ordinary parabola. That's x squared. But x squared minus 2 would shift the picture down by 2 units. So it looks like this, where this goes down to negative 2, right? And then these two numbers, in reality, they are the square root of 2 and the square root of, negative the square root of 2, right? We're finding where x squared equals 0. That is to say, i.e., the x-intercepts. Right? That's sort of a synonym for the roots of a function. They are the same as the x-intercepts, where the y value equals 0. So what we're looking for is this point, all right? The idea behind Newton's method is, here's the concept. You start with a guess. You start by guessing what you think the answer is. Your guess does not have to be very accurate because that's only where you begin. I'm gonna try and write this out very vaguely. Start with a guess, then zoom in and follow the tangent line. All right? So let's say in this example, if you were really looking at this graph, let's say you drew it on graph paper or something, you would realize that 1 is here and 2 is here. Like the true square root of 2 is something like 1.4 something or other. So if you were to graph this, you would see that this number is somewhere in between 1 and 2. And so it would be reasonable in this example to just guess maybe it's 1.5. Like that's not what it actually is, but it's in between 1 and 2. So maybe I'm going to start with this guess. And the idea is I'm going to be continually refining my guess, like making a new guess over and over again, and every time I do it, it's going to get more accurate. So my first guess I'm going to call x1, x sub 1. This is just where you begin. The idea is you begin by guessing, and then you zoom in. So if I were to look at the graph, where this would look like, right here is 1.5, right? It's a little bit bigger than the true square root of 2. I said start with a guess, then zoom in and follow the tangent line. You ready for this? I'm going to zoom in. Whoa, look at that. When I zoom in, I can now look where 1.5 goes to this point. Draw the tangent line at that point using your knowledge of derivatives, whatever. That's the tangent line at that point. And then follow the tangent line means go down to here and choose this point. So this was x1, my initial guess. That's x2, my improved guess. But x2 is not a guess anymore. It's just, you can calculate it by following the tangent line over from x1 down to the intercept of that tangent line, all right? That's x2. How do I get x3? You zoom in again. Now I'm already zoomed all the way in, but in order to get x3, you would go up to this point where x2 goes, draw the tangent line there. I'm not going to draw it because it's going to look all crazy. Draw the tangent line there, find the intercept of that tangent line, and you get a point that is actually very, very close to the actual square root of 2. And if it's not close enough, you just keep on doing it again, all right? That's the idea. So you start with x1, which is a total guess. But then you can calculate x2, and x2 will be even closer to the square root of 2. If that's close enough, you can stop. If you want it to be even more accurate, you would do the same procedure again, all right? This is Newton's method. Now, I don't know how, this sounds like maybe it's going to be pretty complicated. It turns out there is a bit of work we have to do to get there, but all these tangent lines, whatever, is going to boil down to what ends up being a very simple formula that you can, if you want to calculate these numbers, you can just plug into the formula over and over again. And it will very quickly give you super good approximations to what you're looking for. In this example, the square root of 2. All right, so let's see if we can do this. We got 10 minutes. This is enough time to come up with the formula for Newton's method. So my question is, what exactly is x2 in terms of x1? Right? The idea is you just guess x1 kind of out of nowhere, and then you're going to hopefully plug that into some formula and get x2 as the answer. And if you want to, you can plug x2 into that same formula again, and you'll get x3, which is an even better answer, and so on. So what exactly is x2 in terms of x1? Well, I'm going to try and draw this picture again. I'll just draw it as the zoomed in thing. Let's say that the graph goes through here. My initial guess maybe is here, x1. Then I go up to this point, I draw this tangent line here, and then this x-intercept is x2, all right? So what exactly is x2? I want a formula in terms of x1, and it's going to involve, of course, the function, the original function is f of x, right? Anyway, this line right there, this is the tangent line to f of x is the function at the point whose x value is x1, and the y value is whatever the y value is. I will say f of x1, right? Like this point right here, its coordinates are x1 comma f of x1. Sorry, I'm rating too small. All right. What's the formula for that tangent line? Well, we would typically find that using the point slope form. There's going to be a lot of variables here, but this line I'm going to use the point slope form. Remember, it's y minus y naught equals m times x minus x naught, where the m is the slope, and the y naught and the x naught are the coordinates of the special point, which is this one right here that it goes through. All right? And so in this example, using my point slope form, we get y minus y naught, which is the y value of the special point, is f of x1. Y minus f of x1 equals m. What's the slope at that point? Well, the slope is given by the derivative. It is the derivative with this point, this x value plugged in. The slope right there is f prime of x1, right? That's the slope at x1. That's the m, and then I go parentheses x minus x0. X naught is my special point right there, which in this case is called x1. All right. This is the equation of that straight line. What exactly is x2? x2 is the x-intercept of that line. How would we find the x-intercept of that line? Anyone remember how to find the x-intercept of something? I have this formula here. It's got a lot of variables in it. Is it too late in the week to ask how to find the x-intercept of the line? Yeah? Yeah, it's when the y is 0, right? You would typically set the whole equation equal to 0, although I didn't even solve my equation for y there. But yeah, the x-intercept of this line, we would set y equal to 0 and then solve it for x, right? That's supposed to say x2. So let's do that right here. I'm going to use 0 for the y. It says minus f of x1 equals f prime of x1, x minus x1, and I want to solve that for x now, which is not too complicated. You got to distribute the f prime on the right side. Actually, don't do that. Let's just divide both sides by this f prime. It will say negative f of x1 over f prime of x1 equals x minus x1, and then solve for x. You add x1 on both sides. It will say x1 minus f of x1 over f prime of x1. All right? And that's what x2 is. X2 was supposed to be the x-intercept of that line, and that's what it is. So this is x2. This is what I was referring to before. A very simple, it amounts to a very simple formula. So when you're doing the Newton's method, you don't think about all of that stuff that I just said. You just remember this formula, which is very easy to remember, I think. You make a guess, that's x1, and then you just do this, x1 minus f of x1 divided by f prime of x1. And that gives you x2. So generally, we keep on plugging in to get better and better approximations. What I mean by that is, you guess x1, but then you calculate x2 is x1 minus f of x1 over f prime x1. That will be more accurate than your initial guess. If you want it to be even better, you plug in x3 into the same, you plug in x2 into the same formula, right? Like this. You use the x2, you do the same stuff with that, and it gives you the x3, which will be even more accurate. And I will just say, etc. You keep on doing this over and over again until your approximation is as close as you want it to be to the true answer. So I'm going to put the general formula in a box here, which you should memorize eventually. Although let's say, since I've only been doing this for the past 10 minutes, let's say this is not going to be on our test next week, but generally this is the formula. X xn plus 1 is xn minus f of xn divided by f prime of xn, right? This is how you get the next guess if you already know the previous guess. Plug it into this formula like that. All right? That'll do. We'll do a lot of examples using this formula.